All right, this is going on page 31 when we're done, right? So we are looking for domain and intercepts of rational functions, but first we are going to revisit slant asymptotes, right? What is another word for slant? Oblique, yes, oblique. Okay, oblique. Oblique asymptotes, slant asymptotes, they can be called either one, they mean the exact same thing. All right, so let's think about what we can find so far with, or what we did the other day so far with our rationals. The first thing we would want to do is factor, right? So the denominator is going to stay x plus 2. The numerator, I can factor into x and x. 3 is positive, so the signs are the same. 4 is negative, so it's negative, negative, negative 1. Oh, not a 4. Negative 3. Right? We good? All righty, so then from this, do I have any point discontinuity? No, there is none. Why isn't there any? Because nothing cancels out, exactly. All right, so then the next thing we looked for were vertical asymptotes. How many do I have? One. And they are equations of lines. They are vertical lines, so it's an x equals lines. X equals what? Negative 2. Okay, those come from the denominator, right? We all good with that? Okay, so then the next thing we would look at would be a horizontal asymptote. Now, is this function top heavy, bottom heavy, or tied in degree? Top heavy, okay? And you can figure that out from this form or this form, whatever, but it's top heavy. So if it is top heavy, what does that tell you about a horizontal asymptote? Yeah, it's not possible. We don't have any. So if it's top heavy, this is none, which opens the door for a slant asymptote. We know before even trying to look whether or not we have one, because if it's top heavy, it can only be top heavy by 1. So that's a second degree in the numerator, first degree in the denominator. That's top heavy by 1. I will have a slant asymptote, okay? I can have multiple vertical asymptotes. I can have an infinite amount, actually. You can have multiple horizontal asymptotes. We are not going to come across that, okay? I want you to know that it is possible, but that's not something that we're going to encounter with what we're doing. And same kind of thing with slant. But these two are never going to exist together because just the nature of what they are. I mean, if it's top heavy, the answer is none, and it has to be top heavy to be slant asymptote, so they can't exist at the same time. But you can have vertical asymptotes with any of those. So then what do we do to actually find this slant asymptote? Long division. So we're going to divide. Let's come over here and we're going to take x plus 2 and we're going to divide it into x squared minus 4x plus 3. All right. So x squared divided by x is x. Multiply that back. Then what do I do next? Change the sign. Say that to yourself every time so that you don't forget. Those zero out. That gives me a negative 6x plus 3. So then that gives me negative 6 right there. And then that's all I have to do for my slant asymptote, right? Because I don't care about the remainder. So y equals x minus 6. That is my slant asymptote. And it's a y equals because it is an equation of a line. Now, one of the reasons we are revisiting this is so that we can talk about the remainder and what it means. So we're going to continue this one over here and actually find our remainder. So when I multiply this back, I'm going to get negative 6x minus 12. And then I change the signs. So this gives me 15. Which means my answer is y equals x minus 6 plus 15 over x plus 2. This is what I actually get when I divide that, which means that this equation and this equation are actually the exact same thing. They're just different forms. It's like taking 4/3 and dividing that. I divide 3 into 4, right? It goes once with that's 3, and then I get 1 left over. So that's where that 1 1/3 comes from, right? Same thing as 4/3. So that is the same thing as this. Looks completely different though. So that's one reason why we ignore the remainder, because then it would be the exact same function. But let's talk about what this is. Okay, so your remainder is 15 over x plus 2, right? This is our remainder. What this is, so if you look at this function, do you see how the curve itself here versus here, it's farther away from the line here than it is here? You see that as it gets closer and closer? Okay. So remember, the whole idea of our end behavior, our horizontal asymptotes and our slant asymptotes, is that way out at the ends, our function's getting closer and closer and closer to these lines, like infinitely close, just not really, really touching. So the fact that it's getting closer should make sense, right? So what this is the distance between function and slant asymptote. So I want you to think about, as x gets bigger, that means the denominator gets bigger, which means that fraction gets smaller, right? So as x gets bigger and bigger and bigger, that fraction gets smaller and smaller and smaller, and that's why this distance here between the two gets smaller and smaller and smaller and gets closer and closer and closer, okay? You will probably never be tested on that. Honestly, I'm not sure that I was ever actually even taught that. But a few years ago, Ackerman and I were talking about this, and I just said something about we ignore it. So I was like, do you even know why we ignore it? Like, I'm just always, sometimes you do things because your teacher said so. And that's a lot how I learn stuff. My teacher said I ignore it, I ignore it. I just, whatever, I just went on with life. But then we sat there and thought about it and figured it out. Sometimes we geek out on math and stuff like that. But we figured it out. We were very proud of ourselves and very excited when we figured out what it was. Then we Googled it to make sure we were right. But that's what it is. So it does have a purpose. It's not like you just, the remainder, we don't care. But there's a reason we don't care, and there is a purpose for it. Again, I'm not going to test you on it. I know some of you might kind of find that interesting. Some of y'all probably don't care, but I'm going to tell you those things anyway because I think it will interest some of you. Or actually, I know it does, but some of y'all don't even want to admit it. But, all right, we good so far? So that's just a little FYI. Good to know. Let's talk about what we're really doing today. We are looking for the domain, all right? Domain is the set of which kind of values? X, also called our inputs, right? And it's fine to think of them as their X's, but nah. Still training myself more to say input more often. So when you find the domain, it is the first step. First step, you do it before reducing. That's important. Okay, so before we look for point discontinuity. So it's really the very first thing that you're going to do, because if you do it after point discontinuity, then you might miss out on some things. Remember that polynomials, their domain are always all real numbers. Okay, we're going negative infinity to infinity for a polynomial. Rational functions is a polynomial divided by a polynomial. So their domain is all real numbers except for the wholes and the vertical asymptotes. Those are the two things that affect domain. So it will always be all real numbers except point discontinuity and vertical asymptotes. Okay. Then we have our zeros, roots, solutions, intercepts, whatever. But you do this after reducing, all right? And when we reduce, what are we looking for when we're reducing? If I can cancel wholes or point discontinuity, so that means this is after point discontinuity. Now, when we found vertical asymptotes, where did we look for the vertical asymptotes? Where do we look in our function for the vertical asymptotes? The denominator. So your vertical asymptotes are the zeros of the denominator, right? Your zeros of the function are the zeros of the numerator, Okay, zeros of the denominator give you your vertical asymptotes. Zeros of the numerator give you the zeros of the function. So we're finding that means we want to find the zeros of the numerator. Okay. Now for zeros or our x-intercepts, we can have 1, 2, an infinite amount, whatever. But y-intercepts, how many can I have of those? Just one, because if I have more than one, then it's not a function, right? Think about that. If you have more than one y-intercept, it's not going to pass that vertical line test, right? So you can only have one y-intercept if you have one. Sometimes we might not have one. So we also do this after reducing, which means after finding PD. And the y-intercepts occur when what is 0? X. So we substitute x, oops, no, we don't substitute x. We substitute 0 in for x and solve for y. So that means we are looking for f of 0. You need to understand everything in function notation. Okay, f of 0. We're substituting in 0 for x. Any questions at this point? All right, good deal. Now we're going to find the domain. No matter what I'm doing, I still want to start by factoring. So I'm going to factor the denominator because the numerator is what it is. The denominator is going to be x plus 2 times x minus 2. Okay. Now, can I reduce this? Yes, but I'm not going to because I'm looking for the domain. So before I reduce, I look for the domain. And the domain comes from what the function can't be. That's how we figure it out. What the function can't be is whatever makes the denominator 0, right? So x cannot equal -2 or 2. Y'all agree with that? That's what x can't equal. So then to write my domain in function or in interval notation is very easy. I'm starting with -∞. I'm going to -2. Then I have to skip over -2, keep going to 2. Then I got to skip over him and go all the way to infinity. Okay, so you had 2 things you had to skip over because those are the things that x can't be for one reason or the other. Right now, we're not even worried about what that reason is. Okay, everybody good with that? All right. So can I factor number 2? No. All right, so then what can x not be? -11, because that's what makes the denominator 0, right? So then that means my domain goes from -∞ to -11. I skip over that and go to infinity. What questions do you have? We're all good? Okay. So number 3, let's factor this. Numerator and denominator are both what? What are those called? Difference of squares. They are perfect squares, but like it's the difference of squares because a perfect square trinomial is something else. But do you really have to know what it's called? No, as long as you know what to do, it's fine. So x plus 3 times x minus 3 over x plus 5 times x minus 5. All right. Do I care about the 3's right now? Nah. But I know that x cannot be -5 and 5. So write out your domain. I think you can do it without me. Any questions about domain? We're good? All right, moving on. So now let's talk about the zeros. Still, first thing I'm going to do is factor. So we got x plus 2. And then down here, 8 is negative, so the signs are opposite. I think it's going to be a positive 4 and a negative 2. Okay. Now, do the zeros come before or after reducing? After. So this time I do want to try to see if I can. I can't, all right? So if all I'm looking for is the zeros, if I've already tried to reduce, then I don't care about the denominator right now. I'm just looking at the numerator. I put x plus 2 equal to 0. So x equals negative 2. Do you have to write x plus 2 equals 0? No, but I did this first time just so we don't lose anybody. And so I'm going to put a z for my zeros, and that is x equals negative 2. If I asked you for the intercepts, intercepts are written as ordered pairs. Zeros are written as a list of x values. Okay, it's just a different way to express them because they don't have the exact same definition, but they represent the same thing on the graph. Okay. So, any questions? All right, number 10, let's factor. So in the numerator, it'll be x plus 4 times x minus 5 over x plus 4 times x minus 4. All right, can I reduce this? Yes. So I'm going to cancel these out. That means that x plus 4 equals 0 is something that I got to look at. So then that gives me x equals negative 4. That is my point discontinuity. Again, I know it's not asking me for that, but I don't want to ignore it and then you forget to even do anything with it. So that's my x value. We'll get to the rest here in a second. So that means my reduced g of x is x minus 5 over x minus 4. So then let's find our y value here. So I'm looking for g of negative 4. This is negative 4 minus 5 over negative 4 minus 4. So that's negative 9 over negative 8. 9 over 8. Okay. Everybody with me? We still haven't answered the question that's even being asked, right? We are looking for our zeros. Those come from where? Numerator. So the only 0 I have is x equals what? 5. Yeah. Okay. Any questions? All right. Okay, number 3. I can't factor. I can't reduce. My zeros come from the numerator. Do I even have any variables there? No. So do I have any zeros? No. So we got to know how to answer this question because we don't put none for this. We either put x equals, and then your little squiggly brackets, which are empty because it literally means the empty set. Looks like that. Okay. Or another way to write it is x equals, and it's a 0 with a line through it. So every year I have a couple of students, this year is the same, that when you write your zeros, you put lines through it. You're not saying what you think you're saying. That isn't a cutesy 0. It means empty set, which is not the same thing as 0. So don't go doing that on math stuff because you're wrong, okay? It doesn't even make any sense most of the time when you're writing that. So you have to change that in your handwriting. We will probably use the little squiggly brackets more. You might see that more, but that does mean, both of these mean empty set. And in Delta Math, if you have an empty set, this is how you will answer that question. You just literally leave it empty, like leave your answer blank. But here's what you don't do for sure. It is not x equals this. That means the empty set of the empty set, which really doesn't make any sense. Okay, so it's one or the other, preferably the first one. Is how I'll do it. And I will start counting things wrong when you put your zeros with your lines through it, because you're not mathematically correct. All right, any questions? All right, so let's factor number 4. Let's see, I'll have x plus 2x minus 4, and then x plus 3, x minus 3. So how many zeros do I have? 2. So my zeros, the x equals -2 and 4. Okay. Any questions about zeros? No big deal, right? But again, you have to be able to factor accurately and efficiently, which is a problem for some of you. You also, one of the things that a lot of you have been missing on these retests is you're getting some of the answers wrong, because the simple numbers that you're trying to add and subtract, you can't add and you're not adding and subtracting your positive and negative integers correctly. So you're saying things are increasing when they're decreasing, and vice versa. And those are basic math skills. You can understand the pre-cal all day long, but if you can't add and subtract correctly, you're not going to get the right answers. So be very careful with that kind of stuff. All right, so now let's talk about the y-intercepts. This also happens after reducing. Okay, on number 1, I can't factor or reduce, so I'm good. So I'm looking for g of 0. That is 0 minus 3 over 0 plus 11. So my y-intercept, and since it is an intercept, right, like the others, yes, the zeros and x-intercepts, they kind of mean the same thing, but those were zeros, so they were a list. Y-intercept is going to be an ordered pair, and you have to put the 0 in the correct place, and then that's just -3 over 11. That's it. It's that easy. Okay. Good? All right. Need to factor here. So this is going to give me x plus 3 times x minus 3 over x plus 3. Can I reduce? Yes. So these cancel out. X plus 3 equals 0. So x equals a -3. That means I have point discontinuity, and my x value is a -3. All right. My reduced function, f of x, is x minus 3. So then I have f of -3, so I can finish the whole there. This is -3 minus 3, so that's -6. Now what I'm really looking for here is the y-intercept. That is also an ordered pair, but that has a 0 as my x value. So that means I want f of 0. Oh, that looks like a 6. F of 0 is 0 minus 3. So that's -3. Okay. Any questions? All right. Can I factor 3? No, right? And then there's nothing to reduce. So I just need to find g of 0. That's going to give me 1 over 0 squared. And what is 1 over 0 squared? Undefined, yes. You cannot divide by 0, right? It is undefined. So I do not have a y-intercept. It is possible not to have a y-intercept. So in this case, your answer is just none. An empty set wouldn't make sense here because your answer isn't a excuse me, isn't a set of numbers. It's just none. If you need to remember the zero rule, look at those two posters up there. N over 0 is no. That's undefined. O over k, 0 over k is 0. You can have 0 in the numerator. That gives you 0. 0 in the denominator is undefined. Doesn't work. Okay? We good? All right. So go ahead and let's factor this numerator. I have x, and the signs would have to be the same. They both have to be negative. What are two numbers that multiply to give me 11 that combine to give me -3? There's nothing, right? So I can't factor it. If I can't factor the numerator, do I even care right now if I can factor the denominator? No, because if I can't factor the numerator, I'm not going to be able to cancel anything out. I would need to try to factor the denominator to look for vertical asymptotes, but nobody's asking me for that here. So I can just, forget that. What I need is I need g of 0. Well, guess what? If I substitute a 0 in for x, all the 0 terms just 0 out. And so I'm just left with my y-intercept, which is 0, -11 over 4. What questions do you have? Anything? We good? All right. So y'all got about 15 minutes left. I want you to get started in Delta Math.